Hi everyone. Today, I'll present on IoT networks, architecture, and communication standards in agriculture. This is a fascinating field where IoT is driving revolutionary changes in farming practices. My presentation is based on the work of Farouk et al., who explored how IoT architectures and communication protocols are tailored for smart farming. Let's get started. So smart farming leverages IoT devices, such as your smartphones or the drones or the sensors, to tackle global agricultural challenges such as food security and resource optimization. From monitoring of the soil conditions or the weather conditions to automating irrigation, IoT enables more efficient farming practices. Today, I'll cover two major components: the 5-layer IoT architecture designed specifically for agriculture, as well as comparing communication protocols that make these systems work seamlessly. For IoT devices, normally they will have 4 layers: the physical layer, the network layer, the transport layer, and finally, the application layer. However, for agricultural applications, a 5-layer architecture for IoT devices is used, and an additional adaptation layer is introduced to this layer to enhance data transmission over low power networks. Let me briefly go through how each layer works. For the physical layer, this is where data is collected using sensors such as soil, moisture, temperature, and pH sensors. These sensors are designed to operate in low power networks such as your IEEE 802.15.4. For the adaptation layer, this is unique to the agricultural IoT, whereby this layer enhances the data transmission over low power networks such as Zigbee or LoRaWAN, which will be explained later. Network layer will consist of IPv6 and RPL protocols to handle data transmission. The RPL protocols organizes devices in a hierarchical manner called a DoD-AG to prioritize energy efficiency and reliability. For the transport layer, this layer balances speed and reliability using TCP for critical data and UDP for faster data streams. For example, drones may use UDP for live video feeds, combining RTP and RTSP for the live video feeds, and TCP for critical control commands. For the application layer, protocols such as MQTT are used to exchange data efficiently, even in low bandwidth environments. Moving on, let's compare two key communication protocols: long-range wireless access network, or known as LoRaWAN, and narrowband IoT, NB-IoT. Both of these are long-range and low-power networks. However, even though they may seem similar on the surface, they actually have slightly different use cases. LoRaWAN operates on unlicensed spectrum, making use of long-range modulation techniques. It consists of several entities as shown in the figure, from the end devices to the gateways to the network server and lastly the application server. The flow of the communication can be both upstream and downstream in order to pass data within the network. On the other hand, NB-IoT uses licensed LTE spectrum, which is used to power our mobile phones. As such, it offers higher data rates and reliability, ensuring that it is suitable for for urban farming or precision agriculture, with features such as power saving mode and extended discontinuous reception, which allows it to balance uptime and energy use. To compare them side by side, we can see that even though LoRaWAN and NB-IoT both are long-range and low-power options, there are many differences to both. The data rate of NB-IoT is much higher than LoRaWAN since it leverages the LTE technology, and hence it is more suitable for applications where higher data rate is preferred, such as in urban settings compared to rural settings. In conclusion, IoT technologies are transforming agriculture, enabling smarter and more efficient systems. Understanding the nuances of IoT architectures and protocols is critical to optimizing the application. LoRaWAN and NB-IoT are both vital tools, and their selection depends on factors like geography, cost, and data requirements. Thanks for listening.